In this video, we'll cover a series of example programs that demonstrate list processing operations, starting with the range function, which creates a list of numbers between two values. So something like define range AB, where A is the low value and B is the high value. So we'll create a recursive solution to this problem, which means we're going to build this list one element at a time, one value at a time. But recall that when we're building up lists, and we're adding elements into lists, when we const to the front of a list, that works out well. But if we const to the end of a list, it doesn't work so well. What that means is in our solution, we need to start with the end of the list, which would be an empty list, and build toward the front one element at a time. This sort of works out pretty conveniently on a recursive stack. We're essentially going to build up a bunch of deferred adds onto this list, and the first add that actually gets processed will actually be the last one that we schedule, so the very last element in our list. So, to that, if we're creating a recursive function, we have two parts. We have a base case and a recursive case. So if, and in our base case here we'll say A and B will start where A is, we'll just assume the low value, and B is going to be the higher value. And each time through this repetition, this recursion here, we'll add 1 to the value of A, so it gets bigger and bigger and bigger, and eventually it reaches and surpasses B. So what we'll say is if A is greater than B, then we've reached the base case. If somebody asked us to give me the range between 20 and 5, let's say, well, in that case this would be true, and that range would be empty. So we'll give them back an empty list. Now, in the recursive case, we need something that moves us towards this base case, and as I mentioned before, this is going to be our initial value. Then we'll have some sort of increment, so we'll call the range function with A plus 1. So A is going to get bigger each time, and B can just stay the way it was. It's always just going to be the upper bound. So this gives us our initial value, an increment towards some sort of end condition, and the result when we get to that end condition is an empty list. So this gives us most of the engine of this function. What we need now is to do the actual work where we're building up this result list. So we have the starting point, the kernel of our result list here, which is this empty list. So think in terms of recursively, the instance of this range function that would return this empty list would return it back to this function call here normally. So let's say we wanted the range between 1 and 10. This is the very last call where A was 10, so we'll add 1 to it, and now it's 11. 11 is greater than 10, so that we'll return the empty list here. So this thing here becomes that empty list. So what we'll do now is cons on the last value that we have onto that empty list. Now the value that's going to be changing through each instance is this A value, so that's the one that we'll add on there. So cons A to this empty list, and that's actually the entire function. So if this is the empty list, we'll cons 10 onto it if we're assuming 1 and 10 here. If it's a list with the value 10 onto it, then we'll cons 9, and then we'll have 9, 10, we'll cons 8 onto it. So let's test this out, then we'll actually walk through substitution model and see how that looks. So we have the range function from 1 to 10, let's say, and there you go. We get a list of values between 1 and 10. So substitution model for this, we'll use a smaller example so we don't have to do this for too long. So we'll say range 1 to 5, let's say. And in the substitution model, we walk through the steps of the eval apply. So we evaluate all the sub-expressions. They're pretty much as simple as they can be. So then we go on to the apply function, or the apply part, which says apply this range function, which says take the body of this and apply it to the values 1 and 5 for A and B respectively. So we'll jump to the active branch of this loop here, rather than taking the entire body every single time. I think that's enough there. That closes the range, closes the cons. Okay. Where A is set to the value 1, and B has the value 5. So we can simplify this a little bit. So we get cons 1, range 2, 5. So notice we're consing 1 onto essentially a call to the original function with fewer values. And that whole pattern repeats. So we get cons 1 to cons 2 to range 3, 5. And cons 1 to cons 2 to cons 3 to range 4, 5, skipping a couple of steps there in the middle. 1, 2, 3, 4. And then one more, cons 1 to cons 2 to cons 3 to cons 4 to the range 5, 5. Oh, we got a couple more actually. 4, 3, 2, 1. And this whole thing again, cons 2, cons 3, cons 4. So range 5 to 5, we haven't hit this base case yet because that's only when it goes above. So we'll say cons 5 onto the range, from 6 to 5, 6, 5, 4, 3, 2, 1. And then, rather than typing this out, it's gotten a bit ridiculous. Now we're at the base case. So if A is greater than B, we'll return the empty list, which means this essentially becomes that branch, which is just the empty list. And now we can actually just see that this is the exact structure of a list. So cons 1 to cons 2 to cons 3, all the way down to where we have an empty list here. That is just the structure of a proper list. So the final result would be something like that. So notice on the call stack, we're building up all of these deferred operations. We have cons 1, cons 2, cons 3. None of that happens until we get to the very last value. Once we have that empty list, then the first cons that happens is consing the last value into that, and then the value before that, and before that, and before that. So maybe just show one more step here. We'd have cons 1 to cons 2 to cons 3, cons 4 to the list 5 empty list. And I'll actually just put the list here so we can see it. That's 5, 4, 3, 2, 1. Okay, so something like that. We end up with a list that looks something like that. Oh, sorry. When you use the list, you don't need this part. Okay. All right, so that is the range function. Now, this is a recursive solution, right? We build up all these deferred operations on the call stack, but we could also attempt an iterative solution to this problem. So let's try that. So let's create a new function, define range it from A to B. So again, this function will return a list of integers between the values A and B, where A is the low value and B is the upper value. But in this case, we're going to do so via an iterative process. Now recall, an iterative process arises from a tail recursive procedure. That is to say, a procedure that calls itself, but as the last thing that it does. So, a common pattern when we have an iterative procedure is to have a helper function, because we're going to need at least a new variable to hold the sort of temporary solution that builds up each time through our iterative loop, if you will. So we'll say define helper. Now in this case we'll have two variables. They very much represent loop variables, so we'll have a variable I, which will be our counter, and L, which is the result that we're going to be building up over time. Our final answer will be in that variable. So it's still a recursive procedure, still a function that calls itself, so it still needs to have a base case and a recursive case. So we'll have if statement here. And in the base case, we're going to have this variable I that's growing. So much like in the previous recursive function, when our counter variable got too big, then we knew we were done. So we'll say when I is greater than B, then in that case, we're done doing all of the processing. Now remember, one of the characteristics about an iterative process is that it does all of the work that it needs to do and then calls the next instance, which is to say there's not going to be any work left to do once we've reached the base case. This temporary variable will be built up one instance at a time, and once we reach the base case, it will be the final answer. So in this case, we can return L. That'll be the temporary answer will be the final answer once we've gotten to that point. Now, it's up to us to get to that point, so let's try that out. The next step is to make the actual recursive call. Now again, since this is a tail recursive call, the outer function will be the last thing that's done. In this case, needs to be the recursive call. So helper calls itself, and then the values for the variables are what need to be filled in. So a new value for I, we can say I is just going to be incremented by 1 each time through this quote-unquote loop. And now we need a new value for L. So we assume that L starts off as this empty list, and each time through this helper function we want to add one new value onto that list. So the value that's changing over time is I here, so we're going to say cons I to the list. And now this is placed in the argument position that will land in the next instance's L parameter there. Right, so we can close that, close the if, close the define. So this sort of represents what you might call a for loop from another imperative language. In this case, we have the increment with each stage through the loop. We have more or less the loop body itself. We're building up this value on I, and then we have the end condition for when I reaches too big of a value. But what we don't have is the initialization. So this outer function range it, its only job in this case is to create this iterative engine helper function here, and then to initialize it. So actually call it with some initial values. So we'll say helper, an initial value for I, Well, if we want the values between A and B, then the first value of I should be the first value in our range, which would be A. And now the initial value for L, this is again this list that's going to be built up out of nothing, so we'll start with an empty list, and then each time through the loop it's going to cons one new value into that list. So let's try this out. We can run our code here and range it from 1 to 10. And we get the list of numbers from 1 to 10 just in the wrong order. So the wrong order here might be because we're doing this consing backwards. So we had consing some integer onto this list L. You might be tempted to switch the order of these two things, right? So we had an empty list, then we had the value 1. So let's actually draw this out. We had this empty list, and then we added the value 1 onto it. And then, sorry, let's keep this back where it was so we can see the code while I'm doing this. There we go. So we had the empty list, and then we added the value 1 onto it, and then the loop came around again. I was 2, and we said cons that to the front of the list. And then we said cons to the front of the list again, and cons to the front of the list again. So eventually this list builds up with all the values in the wrong order. So you might be tempted to do something like this, where we say cons li, but as I mentioned earlier in this video and in the previous video, consing to the end of a list doesn't really work. If we have an integer and a list and we want to join them together, the integer should always be in the car position of the cons, and the list itself should always be in the CDR position of that cons, for reasons that we've seen before. But let's see what happens if we run it this way. So save our code, run it, range IT, and then we get that sort of transpose looking list where the empty list is at the beginning, all the values are in there, but they're not structured properly, so we can still see all the dotted pointers in the middle as well, or dotted pairs rather. Okay, so how do we fix this? Well, there's a couple different solutions. The most elegant, though, I think, is to just start with the value B and count down. We can cons to the front quite easily, right? We saw if we left this the way that it was, it created a proper list, just the values were in the wrong order. So let's traverse that range in the opposite direction. So we'll start with the value B as our initial value. Instead of counting up with each step, we'll count down with each step. And then once we've reached the end, we'll have reached the smaller of the two values. So this will be an A, and our comparison will be in the opposite direction, because we're counting down. So let's save, run, and try that. That's a real easy solution. So in this case, we're doing the exact same work here. And let's actually walk through the substitution model here. So I'll do a smaller range so we don't end up stuck in this loop for too long. So range from 1 to 4. The very first thing that does, range it from 1 to 4. The first thing that does is defines this helper function, and then it calls helper B an empty list. So we get helper B, which is 4, and an empty list. Okay. Then the helper function comes into this where there's our base case. That's not true yet, so we'll just jump to the active branch, and that call to helper becomes another call to helper where it was 4, so it's still 4 now, I guess, and cons 4 onto an empty list. Okay. We can simplify that down a bit before going to the next step. So we get helper 3, and then cons 4 to the empty list is just the list 4. Similarly, continuing on, so we called helper with the value 3 and a list with a single value in it. So I is 3 and L is a list with that one value. And then we do the exact same thing. So we end up with helper, I'll do one more expanded step here, 3, 1, and then cons 3 onto the list 4. Close, there we go. Right, and that simplifies to helper 2, list 3, 4. And as you can see, this pattern continues on. So we get helper 1, list 2, 3, 4, and I guess that'd be helper 0, list 1, 2, 3, 4. At that point, I is less than A, which was 1, so it returns the list. And as we can see, the thing in that variable position is the completed answer, so it returns the list 1, 2, 3, 4. So that's the range function. Let's move on now to the getElement function. So getElement takes in an index and a list and returns the target element specified by that index if it exists. So recall, if we want to find an element in a list, for example, if we want to find the first element in a list, we can just say the car of L. And we saw if we want to take the second element out of a list, so if we had some list, define L to be the list 1, 2, 3, 4, 5, 6. If we want the first element, we could just say the car of L, and that just gives us that item. If we want the second element, we have to CDR down once, and then take the car of that, so the catter of L, and that takes the next element. If we want to take the third element, we'd put 2 CDRs, and then the car, and the next element, etc. So, all of which is to say, if we want to find a specific element in the list, we just need to CDR down the list that many times, and then take the car of the list at that point. So, let's create a function. Oops, wrong window. Define get element. This will take in a list, we'll call it L, and an index, we'll call it I. Okay. So, it's still a recursive function in this case, so we're going to say something like if the item that they're looking for is at the front of the list, for example, so if I is equal to 0, let's say, then it's a really trivial problem to solve. If it's the very first item, then we can just say return the car of L. So if they give us a call to get element with a list with 300 elements and they say return item 0, well, car of L will do, and that's it. Now, our job is to make it so that if they give us a job where I is much higher, we need to work it down, work that I value lower and lower until eventually it does reach 0. At that point, we can take the relevant car. So we're going to call get element here with subsequent values of I, and each time we decrement the value of I, so I minus 1, we're going to also remove one element from the list. So we'll say the CDR of L. So recall that the CDR of L is still a list. It's just a list without the head of that list attached. So that what we're passing in is all of the list minus one element. Oops, sorry, wrong order here. That's for L, that's for I. So all of the list minus one element goes into L. And then because we've subtracted one element, we're also going to subtract one from I because we're getting closer and closer to the point that we actually wanted to get the car from. So we're reducing L, reducing I, eventually we get to the right point, and then we can just return the head of that list at that point. So we can run this and try get element from the range 1 to 200, and take the 14th element. And there you go. Now, this solution is an iterative solution, but as you might notice if you try to solve this recursively, it doesn't really make sense. And the reason for that is that this is a problem of reduction. So let's take a look at the substitution model. Here we go. Something like get element from the list 1, 2, 3, 4. We'll get the tooth element from that. So index 2, which is actually the third element. Okay. So the list 1, 2, 3, 4, we'll say that's as simple as a list looks for now. We'll see actually a simpler representation later on. Get element is this function, and 2 is the integer 2. So we apply. Let's take the active branch because I does not equal 0 because it equals 2. Get element, yes, that's fine. Okay. So we get this, the CDR of L, where L is equal to this list that we passed in, and I is equal to this 2 that we passed in. So to simplify this line, the CDR of this list is this entire list minus its first element, and 2 minus 1 is 1. Okay. Then we call get element with, notice we have a smaller list and a smaller integer. So you can see we're moving closer and closer to the solution for this problem. Oops. Copy, not cut. And paste. And again, we end up with the CDR and I minus 1, so just to shorthand the substitution model here, list 3, 4, and then our I is 0. And then the next call to this, when we call get element with an I of 0, that hits our base case, and we say car of L. So then this line becomes car of the list 3, 4. At that point, we can do that in our heads. Car of 3, 4 is just the first value, which is 3. All right, So as I mentioned, it doesn't really make sense as a recursive problem. That's to say, the recursive solution and the iterative solution both land in the same spot. Because there's no solution being built up, there's no deferred operations to put onto the call stack. We're just shrinking the list. We're not doing anything on the way back down the stack. So once we have the final answer, all of these things can disappear. So there's not really anything to do in this position here, which would create a recursive function. All right. So let's move on now to finding the length of a list. So if we want to find the length of a list, that means we're given some sort of list as input, so something like define length of L. So the key to solving this issue is realizing that we can identify an empty list using the predicate null, or equivalently by asking is it EQ to the empty list. So our base case in this case is asking if our list is null. In that case, we already know the answer. What is the length of an empty list? Well, there's 0 elements in an empty list. No problem. Now all we need to do is take one step at a time, removing elements from that list, and each time we do so, just keep track of the number of elements that we've removed. So there's 2 ways we can solve this, recursively and iteratively. I'll solve recursively in the video. I'll leave the iterative as homework for you guys to solve yourselves. But in a recursive solution, we're going to call this function. So we're going to say length with a smaller version of L, so CDR of L. So we've removed one element from this whole list. Eventually, we'll have shrunk the entire list to be null. At that point, it will return the answer 0. So what we can do is add 1 to that answer each time we called the function. So if we say +1 to the length. So if L was a list with 1 element in it, the CDR of L would be empty. So that would return 0. So this whole thing here would be 0, and we'll add 1 to that. Or another way of saying that is the length of a list is 1 greater than the length of the CDR of a list. And then you can just repeat that process till you have an empty list. So let's actually see the substitution model for that real quickly. So I'll say the length, we'll do a list that's relatively short. The pattern's pretty easy to catch once you see it. So length list 1, 2, 3, so that's this branch here gets used. 1, 2, 3 brackets. Okay. So length of list 1, 2, 3 is +1 the length of the CDR of that list. So if we say this was list 1, 2, 3, let's get all my brackets here. List CDR length plus. Okay. Then we can simplify this part of the expression. The CDR of that list is the list 2, 3. It's the list minus the head. Now if we ask what is the length of that, because we need that before we can do the addition, we would say +1 to, and again we have that same branch, so +1 the length of the CDR of the list 2, 3. CDR length plus. And now you can see each time our list shrinks, we're adding 1 extra plus onto there. Yeah, and that simplifies here, +1, the length of the list 3. Close. And then just jumping the next step here just to be a bit cleaner here. That's the same thing as saying +1, the length of the empty list, so the CDR of that list. Plus. And then finally, if we ask what is the length of the empty list, that returns the value 0. And then you can collapse all of that to the value 3. All right, so again, as homework, I recommend trying this out as an iterative process. Let's move next then to the problem of appending 2 lists together. So let's say, for the sake of argument, that we have 2 lists here. Define L1 to be the list 1, 2, 3, and L2 to be the list 4, 5, 6. So a naive solution for appending 2 lists together would be something like define L3 to be cons L1 and L2. Cons is a nice simple glue. We need to join these 2 lists, so why not just cons them together? Well, let's run this and see what happens. What is the value of L3? So we end up with the list that has all the values, 1, 2, 3, 4, 5, 6 all together, but they're not together in the right way. With append, we want to join these two things into a single list. In this case, we have a list with 4 items, where the first item is a sublist, and then the remaining 4, 5, and 6 as elements. So we want to have all these things in what's known as a flat list, or just a one-dimensional list, if you will. So the cons doesn't work here because if you think of what cons does, it joins, or rather it creates a pair, where in this case the car of that pair points to a list instead of a single element, and the CDR points to a list as it should, in this case 4, 5, 6. So what we need to do instead of just consing the entire list is go through element by element joining. So we want to take the 3 out of this list and join it onto L2. Then the 2 out of that list and join it onto what's left, and then take the 1 out and join them all together. So the code for this sort of works by recursively passing down this list, or CDRing down this list element by element. When we get to the end of the list, then we just start consing the values back up. So something along the lines of define append L1 and L2. So there's going to be a recursive solution, so we need to have our base cases. Now, most of our base cases so far have been when a list is empty, then we know we've done all the processing and we can start building up our solution. In this case, that's going to be true as well, but we don't need to go through both lists. If you can see from what happened when we cons these two things together, list 2 was fine the way it was. The only issue was we couldn't just join everything at once. We had to go through individually, grab each one of these elements out of L1, and then join each of them onto L2. Which is to say, L2 can stay the way it is, and we're just going to join elements or process through L1 to join those elements onto L2. So our base case in this case is that we're done processing just L1. Now, if you think, what would happen if somebody asked me to append an empty list to the list L2? Well, the answer in that case would just be all the elements in L2. All right, so that gives us our base case, and the next case is our recursive case. In this case, we need to, two things. We need to CDR down L1, so make L1 smaller and smaller and smaller, and then cons the solutions back up. So let's start with the recursive call here. We're going to append a smaller version of L1, so the CDR of L1, onto L2. So this is a sub problem. It removed one element from L1 and said call append on that. But now what we need to do is take that one element that we removed and add it to our result. So we'll say cons the car of L1, the element that we removed, onto the thing that comes out of, append the rest of it. So if our list is 1, 2, 3, and 4, 5, 6, the car of L1 would be 1. So we're going to remove 1 out of L1 and then append the list 2, 3 onto the list 4, 5, 6. Eventually, we'll have CDR'd down through all of L1. We'll get back the list L2, and then we'll append the elements 3 onto that, 2 onto that, and then 1 onto the result. All right, so let's test that out. Let's run our code, and we get append. We have L1 and L2 still, so let's just use those. And we get the list 1, 2, 3, 4, 5, 6. All right, so let's see the substitution model for this real quick. We'll use a smaller version so it doesn't take too long, but the substitution model for append, say the list 1, 2, and the list 3, 4. So if we call append with 2 lists, the first list is not null, so we don't hit our base case, and we get this as the next step. So we have cons the car of the list 1, 2, that's L1, onto append the CDR of the list 1, 2 onto the list 3, 4. Close the append, close the cons. All right, so we can simplify the cars and CDRs from that line. So we can say cons, and the car of the list 1, 2 is just 1, onto append, and the CDR of list 1, 2 is just the list 2. Okay, all right, join that to the list 3, 4. That gives us the next line. Now, before we can do this cons, we need the value for this sub-expression, so we have to call append with the list 2 as our first list. That again doesn't hit the base case, so we can follow through in this pattern here. We get cons 1 to cons 2 onto append the CDR of list 2, which is the empty list, to the list 3, 4. Close, close, close. Okay. Now, if we call append with an empty list, that does hit our base case. So we have cons 1, cons 2. Now, if we call append here with this empty list, that's our base case, and that says return L2. So the value of this whole sub-expression is just the list 3, 4. And at that point, we're just consing to the front of a list, which we've seen before. So dot, dot, dot. This collapses down to the list 1, 2, 3, 4. Okay, so we're just building up these deferred conses as we CDR through the list. Eventually, we run out of elements from L1. At that point, we start executing all those deferred conses. So the first cons that happens is the last one that we set up. So we said, there's our base case. Attach the last element in list 1 to the result of our base case. And then we attach the element before that and the element before that, etc., all the way back to the front of L1. All right. Now, since list variables are pointers to actual data, it's worth mentioning here that this L2 variable, or more specifically this L2 variable, is still pointing at the list 4, 5, 6. So if I said append L1 and L2, I get this new result. And we can actually say define L3 as append L1 and L2. And that gives us back this new list, L3, that has all the things joined together, but L2 is still pointing to 3 of those elements. If you think what we've done here, we've created a sequence of pairs where we attached 3 onto an existing list 2. So the pointer was still pointing to that first pair in that list. So L2 still points at the head of this sublist, if you want to call it that. But then element by element, we removed integers out of L1 and attached them onto the front of this L2. So we get this new L3 that has 3 integers and a list, if you want to call it that. It's not an issue since our language doesn't yet have mutable data. This isn't really any worry. But if we did have mutable data and we made a change to these values in L2, we would see that change occur in L3 as well, because there is in fact an alias pointing to the middle of that list there. Just something to keep in mind later on once we do learn about mutable data in this language. Okay, next up we'll take a look at an important pattern that's captured by the problem of scaling a list by a given factor. This is actually it's an instance of a more general problem known as just mapping over a list. The idea is we have a list of values, in this case numbers, and an integer that we want to scale all those values by. We need to go through each individual element in that list and multiply them by that scaling factor and return a list that has the same number of integers all scaled up by the factor. So we have some sort of function here, define scale list. Okay, so this takes in a list, we'll call it L, and some constant factor x. Now, what we need to do is just CDR down this entire list. So we'll do a recursive solution again. We'll say if our list is null. Well, if we want to scale an empty list, that's easy to do. We don't have to do anything. Here's your empty list back. Now, if it's not our base case, then we need to move the problem towards the base case. That is to say we need to shrink this list. So we'll say scale list. And instead of passing in just L, we'll pass in the CDR of L, so we get closer and closer to the fact that L will be null eventually. The constant factor doesn't need to change, it can just stay as X. So again, we have an input list. We're going to shrink it down until eventually it reaches null. At that point, it will return an empty list. So what we need to do now is build up the solution. So if the result of calling scale list gives us back an empty list, then we need to take in attach the element that we just removed onto the result. So if we just removed the head of this list, giving us back an empty list, we need to attach that car back on. So we'd say something like cons the car of L onto this list. But if I just did this, right, if I closed off all the code like this, the code as it stands here would just be would just return the original list, right? It says CDR down and then cons back up. So it's removing elements and then it's attaching those elements in the exact same order that we removed them. Which is more or less what we want. We want the elements to be in the same order, but we also want them to be scaled. So rather than just consing on the car of L, let's cons on the scaled version of that. So we'll say times x the car of L. So now if that was a 1 and x was a 10, now the result will be a 10 and we'll attach that back onto our list. So let's test this out, make sure it works, and then we'll see how it works. So scale list, we'll take in the list 1, 2, 3, 4, 5, and we'll scale it by a factor of 10. And that gives us back 10, 20, 30, 40, 50. All right, so this is an important pattern. So let's see the substitution model of this first. So the substitution model of something like scale list, let's do a simple list like list 1, 2, 3. and a factor of 10. Okay, so we call scale list. This list will just again assume that that's the simplest form for now. We'll see a simpler form to represent list later. An integer is just an integer. So now we apply this function to these arguments. Now, since the body of this function is an if statement, we'll just use the active branch of that if statement, and our new expression becomes cons times x, the car of L, close that, to scale list the CDR of L by x. Close scale, close cons. Okay, where x in this case is now 10. Oops. And this list is the list 1, 2, 3. List 1, 2, 3. Okay. So we can simplify this down a bit by getting rid of the cars and CDRs. So it says cons times 10 to the car of list 1, 2, 3, which is just 1. And then scale list the CDR of list 1, 2, 3, which is just the list 2, 3. Okay. Then our code becomes much more readable, so we have cons 10 onto the result of calling scale list on the CDR, so list 2, 3. And then this pattern repeats. So we have cons 10 onto cons times 10 the car of this new list, which would be 20. Onto calling scale list 3 and 10, the CDR of our list. Close that, close 20, close 10. And then next step, so cons 10 to cons 20 to cons 30. Scale list. The CDR of the list 3 is now the empty list, and our factor doesn't change. So we close that, close, close, and close. Okay. And then we're at our base case finally, so we say cons 10 to cons 20 to cons 30. We call scale list with an empty list, while our base case says return an empty list. So this whole sub-expression here results in the empty list. Close, close, close. And now this line looks like the structure we've learned that creates lists. So we can say this whole thing eventually just becomes the list 10, 20, 30. Okay, so this is a specific instance of a more general pattern. We can distill this scaling integers into a more general pattern of just processing any sort of operation over each element in a list, a sort of for each, if you will. In Scheme, we call this map because it actually returns a list of the exact same number of elements, but with each one of those elements mapped to a new value. Based on some sort of function. So we can make this a higher order procedure that doesn't always just do multiplication, but takes in some general function and applies that general function to each element as it goes. So we can say define the map. I'm going to say the function and then the list, just because it makes the English alliteration easier when you're describing these maps. But the rest of the code is pretty much the exact same. If we're at the end of the list, then mapping whatever function over an empty list just gives us the empty list. You can't modify no values. And in our recursive case, we're still going to cons the car of L onto the result of mapping the rest of our list. But now we're going to use this function f. So we're going to map some function f over the rest of our list, and we're going to apply that function f to the car of our list. There. So in our base case, if our list is empty, great, we're done. In our recursive case, we'll take one element out of our list and apply f to it. Let's say f is multiplying by 10 or doubling or squaring or whatever we want to do to each individual element. We cons the result of applying that function onto the result of mapping that function over everything else. So the substitution model actually looks exactly the same. We call map with some function, let's call it squaring, over these lists. We end up with the deferred operation. This would be f of some value. So let's say, cons. This would be f of some value, so times 10, 1 would be, let's say, times 10, 10 if it's squaring, for example. And the values would all sort of accumulate through these conses one step at a time. So let's actually see this in practice. So if I run this, we could say map some function. Let's do a lambda x times xx. We'll take the square function. We'll map that over the list 1, 2, 3, 4, 5, 6. And then we get a list of the first 6 squares. We can do a similar map. Say map lambda x absx Actually, you know what? We could just pass in ABS. I think that still exists. Let's test if it exists first. It does. Okay. Map lambda x, the absolute value of x, for example. Or in fact, we can actually just pass in ABS over the range 1 to 20. Let's say negative 20 to 20. There you go. And now we have all positive values. So we can use this map function in a nice general way. We can even use scaling if we wanted. For example, we could say map some lambda that takes in an x and multiplies that x by 2 over the list 1, 2, 3, 4, 5. So we can still produce the scaling instances. We saw 10 before. This is now 2. The one trick is the function you're passing in has to be a function on exactly one parameter, because when we say f of the car of L is the only argument that's being passed into that function, so that function can't take in any additional function parameters as well, because it has no application on those additional arguments. All right, our next problem is the problem of selecting specific values out of a list, or filtering over a list. The idea is we want to take in a list and return a smaller list that has just the values that pass some sort of predicate function. So similar to mapping, this is another higher order procedure. It takes in a list as argument, but it takes in a function. This function in this case, though, is a predicate function. It has to return true or false. We'll apply that predicate function to every element in the list. If it's true, we'll keep those elements. If it's false, we'll throw them away. So the code for this actually ends up looking very similar to the map function as well. So we'll say filter. We'll take in some predicate and some sequence. I'll call it L. Now, the structure of this works very similar to map. We're just going to CDR down this list, but we have one extra branch owing to the fact that each element may either pass or fail this predicate test. So in this case, we'll have 3 branches, one for our base case and then 2 recursive cases. So we'll need a cond instead of an if just to keep it clean. We could use nested ifs if you will. So our base case is still if our list is null. In that case, if somebody asks us to filter out all of the even elements from an empty list, we're going to come back an empty list. If they ask for all the odd elements out of an empty list, same answer. It's an empty list. So if the sequence is null, we give them back an empty list. Now, the other 2 cases are the 2 cases of whether or not the specific element passes this predicate test. So the condition is the predicate applied to the first element in our list, so the car of L. So this predicate is something like, is the value even, or is it the number 0, or is it positive, something like that. This takes in the value from our list, the head of our list, and returns true or false. So if it's true, that means it's a good element, we want to keep it. So in that case, we will say cons the car of L onto the result of doing the rest of this filtering work. So filter, pass predicate through, and we want to just filter the rest of the list, so CDR of L. Okay, so if this element passes our test, then we keep it, and we continue doing the work. If it doesn't, so in the else case here, well, we know we have elements, but we know this first element isn't a good one, so it doesn't really matter what happens to that first element. We can just throw it out, but we still need to do the rest of the work. We have to check all of the other elements. So in the else case, we still say filter this predicate over the CDR of L, but we don't cons the value, the car, back into the result. We just throw it away. So we still recurse down, but we don't build up this value into the solution. And let's test this out. So let's run our code, and we could say filter, for example, even, which is a built-in predicate, over the, say, the range 1 to 20. And we get just the even numbers. And we can use that exact same higher order function with a different argument to get just the odd numbers. You could do the same thing with positive, negative, whatever you want. You could create your own predicates and apply them to lists and get back just this filtered list. So it's a very important general purpose list processing algorithm. So let's see the substitution model for this one. If I said something like filter odd over the list 1, 2, 3, 4, 5, bit of a longer one because we have to do a few extra steps here. Then the next step we need to check is whether or not the car of this list passes our predicate. So we'd say something like, our predicate in this case is odd, and we'd ask, does that pass the car of our list? So the car of the list 1, 2, 3, 4, 5. And that's true in that case. So we move on to, so the car of this list is 1, 1 is odd, so the active branch becomes this branch here. So we say cons the car of L, so again the car of the list 1, 2, 3, 4, 5, close, onto the filter of our predicate, which is odd, over the CDR of the list 1, 2, 3, 4, 5. Close, close, and close. Now, we can clean this up a bunch, so we can say cons, the car of L is just 1, onto filter odd over the CDR, which is just list 2, 3, 4, 5. And this pattern sort of repeats, so when we go down to the next one, we call filter odd over list 2, 3, 4. It's not an empty list. The predicate of this, the predicate applied to the car here is predicate applied to 2. 2 is not odd, so we go down to our else case, and we end up with cons 1 to filter odd, and the CDR of that. So that's the list 3, 4, 5. Close, close, close. And then we could say the next one, which is cons 1 onto the result of this. Because 3 is odd, we get this second branch here. So we have cons 3 onto filter odd the list 4, 5. Close, close, close. And then cons 1 to cons 3 to, and then the next value we ask, is 4 odd? And it's not, so we end up with filter odd CDR of that list, which is the list 5. Filter 3 and 1, and cons 1, cons 3. Filter 5 is odd, sorry, so we say cons 5 onto calling filter odd on the empty list, the CDR of the list 5. Close, 3, 1, okay. And then we cons everything together, so cons 3, cons 5. This filter odd in the empty list finally hits our base case, so that gives us the empty list as a result. 5, 3, 1, and that just cleans up to the list 1, 3, 5 in the end. So goes through element by element and defers operations only if the predicate, if the car passes the predicate. In that case, we'll defer a cons. If it doesn't pass the predicate, then we'll just recurse down without building up any deferred operations there at all. And that brings us finally to the problem of summing a list of numbers or reducing a list in the general sense of the pattern. The idea here is we have an entire list of values. We want to collapse them down into a single value, much like if we were to, for example, sum all the values in a list or multiply all the values in a list all together. So the solution here works a lot like map, but instead of consing the values of our result together, we'll apply some other sort of operator. So we're going to need a few extra pieces of information here. So we'll say something like define reduce. This takes in some operator, because we can't assume cons, some initial value, and we'll see why that's important in a minute, and the actual sequence, which I'll just call LIS for short. Now, our base case for this problem is, as it always is, if we've run out of elements, well then we're done. So if our list is null, then in that case, we can just return some value. Now, what that value should be is going to depend on the problem, right? If we want to sum a bunch of values together, then an empty list sum together should give us 0. But if we want to multiply a bunch of values together, well, giving 0 is going to change the answer, so maybe we'd have to use a better value like 1, for example. If instead of doing math, we were maybe consing the list together using reduce, well then the initial value wouldn't be a number, it would maybe be an empty list instead. So this initial value just sort of sets up this recursive process, or the base case of that recursive process. So the initial value here is just whatever's passed in as the initial value. Now, in our recursive case, we need to shrink the problem down. So we're going to take the CDR of our list each time through. We need to build up this solution. So very similar to how our map function worked, but instead of applying cons, we'll apply whatever operator is passed in to the car of our list. Okay, so we'll take the car of our sequence and we'll merge that or join that with this operator to the result of reducing the rest of the list. So we'll say reduce the same operator, the same initial value, and now just a smaller list. So if I want to sum all the values between 1 and 10, and I have a list of all the numbers between 1 and 10, this operator can be the plus value, the initial will be 0. And this says take the first value off of that list, so 1, let's say, and add it to everything else, the sum of the values from 2 to 10, if you will. So let's test this out. Run and reduce. So we'll actually just do that exact example. Reduce with plus and 0, the range 1 to 10. And we get the sum from 1 to 10, which should be 55. Can make it 100. That should be 50, 50. And we can do this with all sorts of other values as well. We could do, for example, multiplication. If we want to multiply all the values between 1 and 10, or 1 and 100 as I have it there, we change the operator to multiplication. But notice if I don't change the initial, we end up with the value 0. The reason being, if we return 0 as our base case, then we're saying multiply 100 by the result of that base case, which is 0. Okay, so that returns 0. And that says multiply 99 by 0, which is still 0. And then multiply 98 onto that, which is still 0. So if we want to actually get a result in a multiplication, we need a different initial value. So we'll say 1 in that case, and that's, I'm going to assume, the correct result for multiplying all the values between 1 and 100. Use a smaller range, let's say 1 to 4. There you go. All right. That's pretty much it for explaining the code here, but to see how this works, let's walk through the substitution model. Again, it works very similar to the map function. We're just deferring these operations. The only real difference is that instead of having a cons operator here, we're having a general operation that's whatever is passed into this function. So we could say reduce plus 0, and we'll say the list 1, 2, 3, something small. So our list is not empty, so we end up in the recursive case. The recursive case says apply the operator, which is the plus symbol, to the car of the list, which is 1, and the result of calling reduce with the operator, initial value, and the CDR of the list. So list 2, 3. Again, our list isn't empty, so when we call reduce on the list 2, 3, we end up with plus the car of the list to reduce the CDR, so list 3, close, plus, plus. Okay. And then we have the same thing again, so plus 1, plus 2. We call reduce on the list 3. That's still not an empty list, so it says plus the car of the list, reduce, plus 0. And now the CDR of list 3 is just the empty list. So we close that, 3, 2, 1. And now we're finally at the base case. So plus 1, plus 2, plus 3. If we call reduce on an empty list, that's going to return whatever the initial value is, which in this case is 0. So it'll say plus 3, 0, close, close, close. And then dot, 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 the whole thing eventually collapses down, and we get 6. Right, so like I said, in terms of the substitution model, it works very much like map. The deferred operations in the map, however, were all of these conses, whereas here we have whatever the operator passed in is. That's what's getting deferred. If we pass in multiplication, then we have a bunch of deferred multiplications. If we pass in a cons operation, for example, we'll have a bunch of deferred cons operations. Now, the reduce function does actually have some analogous names. You might hear it called the accumulate function, or in other languages, other functional languages, you hear it called the fold function. But with fold, there's both a fold L and a fold R, depending on the order of operations. So imagine, for example, or try and picture in your head what the result of this solution will be. If I say reduce, divide by 1, the list 10, 2, and 2. So what is the sequence of operations that will occur if I run this instance of the function? So I'm going to be dividing through each of these values, but the real question is which two values get divided first? So we have this initial value. That's usually where it starts, right? We have all these deferred operations building up, and it's the initial value and the last value in the list that get applied first, right? It's the nested-most combination here. And this is what's known as a fold R, or a right fold, because the rightmost operation is the one that occurs first. So in this case, using this instance of our function, this would end up being something like 10 divided by 2 divided by 2 divided by 1. Something like that. Which 2 divided by 1 is 2, 2 divided by 2 is 1, so 10 divided by 1 gives us 10. Okay. On the other hand, if we did a fold L, or an L fold, if you will, then the operation works a little bit different. We have 1 divided by 10 as the first operation, so we take our initial value and combine it with the head of our list using the operator. And then that whole thing gets divided by 2, and then that whole thing gets divided by 2. So we'd end up with 1/10 divided by 2 is 1/20, divided by 2 again is 1/40. Equals something like 1/40. Okay. So the recursive function we created does in fact create this L fold, or sorry, R fold here. This is an R fold. But the iterative function, if we define a reduce that works iteratively, reduce it, this actually will produce an L fold. It'll operate on the first element of our list, because remember, the iterative versions of these functions, they work a lot like loops as we'd think of them in a regular imperative language. It starts with the first element of the list and processes it. Then it goes to the next element and processes it, leaving no deferred operations. When we have recursive work, we're deferring the first operation first, but it ends up getting done last. So it ends up reversing the order. So we need the same sort of parameters here. We need an operator that we're going to use to combine all the elements in the list. We'll need an initial value, but because this is an iterative process, we'll also need a working total. We can actually use the same variable for this. It'll initially be our initial value, but since it's going to be changing over time, I'll call it the total because it's going to be our working result. And then some sort of list that we want to collapse down. So that'll just be lis. Now the structure again is a recursive function, so we need a base case. We know we're at the end of all the work when our list is empty, but unlike in the recursive problem where the base case sort of signifies the beginning of all of the work, in an iterative process, if we reach the base case, we've done all of the work. We don't have any deferred operations to process, which means the initial value, which has been building up the sort of working total, if we've done all of the work, now it's the final value. So we'll say total here. And then in a recursive case, we need to actually make that into the sort of working total and do the work that takes it from the initial value to the final value. So if this is going to be a tail recursive function, the last thing we want to type here, or the last thing we want to do rather on this line, is call this function, so reduce it. And then we need to create new values for each one of its parameters to set up the next iteration of this repetitive process. So the operator doesn't change, we can just pass that straight through. This total, again, starts as the initial value, but then needs to be grown one step at a time. So each time through, we're going to take the operator and the car of the list and combine them into total. Something like op, total, and car of the list. So if op is plus, and total will be our initial value 0, and the car of our list is 1, that's plus 0, 1, which gives us 1 as the next value. And that'll be plus 1, 2, and then plus 3, 3, all the way down. Okay. And now just to make sure that we're not always processing the same values, instead of just list, we'll say the CDR of list is the new value for the list variable. All right. So let's run this and test it real quick. So if we say reduce, say plus 0, and the range 1 to 10, so summing all the values, but we want to use the iterative version, reduce it. It does the exact same thing, but now in an iterative process. So let's take a look at the substitution model here. We have reduce it, the operator is plus, the initial value is 0, and our list, we'll use a short list like list 1, 2, 3. Okay. Now going to the active branch of the if statement is just another call to reduce it. So we say reduce it. The operator doesn't change. The total becomes the operator, which is plus, applied to total, which is 0, and the car of the list, which is, I'll just type it out here, car of, I'll just type 1 for now. And then the list gets shrunk. It says the CDR of the list 1, 2, 3. Okay. Now we can simplify this line. It says reduce it plus 1 and the list 2, 3. So when we call this function, it's still not the base case, so we end up at the same spot again, but with smaller values. So we have reduce it plus, now this becomes plus 1 and the car of our list, which is 2, so plus 1, 2, which is 3. And the CDR of that list, which is the list 3. And then we call reduce it again, and we add the total and the car of our list, so that's still this line here. That becomes 6. The CDR of the list 3 is just the empty list. And finally, when we call reduce it with the empty list, that's our base case, and it says return total. So we can actually just say 6. Now, notice when we do this iterative version, the very first combination, the very first application that happens is between the initial value 0 and the head of our list 1. Compare that to the recursive version, where the very first application that happened was between the initial value 0 and the end of our list, which was 3. Which is to say, when we do the reduce it when we do the iterative reduce function, it's actually creating an L fold, whereas if we do the recursive version, it's doing an R fold. It's just changing the order of these two operations. So if we change this line here to say reduce it, divide 1, list 10, 2, and 2, then we should get an L fold. There we go. So we get 10 for one of them, 1 over 40 for the other. It's worth noting for this problem at least, if we actually just change the order of these two things, then we'd get 10 divided by 1 divided by 2 divided by 2, which end up with the same answer. So when you're creating the iterative version, if you want to get an L fold, it's important that the initial value is the leftmost value. If you want an R fold, then the initial value should be the rightmost value, as we can see here. All right. That is it for this function, and that's also it for this video. So in the next video, we'll go on to learning more crazy things we can do with lists, specifically once we have lists of lists, or as we'll call them there, trees. And I'll see you in the next video.